Hello dear friends, a great welcome to the series on engineering mechanics. Myself Jayarajan P. This is a class 5 of the series and it includes the following topics. First one, concept of a position vector, applications of position vector, and finally an example problem to demonstrate the application of position vector to a practical problem. So let us start our class. So let us first discuss the concept of position vector. So, as the term suggests, a position vector is used to locate a point in space related to a reference point. For example, referring to this sketch, here is shown a point B whose coordinate is xyz related to the origin O. Now, to find out the position vector associated with the point B, we draw a vector from the reference point O to the point B. And the vector OP, that is designated by vector R, is the corresponding position vector, which can be written as vector R is equal to xi plus yj plus zk. For this case, the position vector is directed from the origin to the subject point. Position vector can also be directed from one point to another point. For example, referring to this sketch, here is given 2 points A and B whose coordinates are xa, ya and za, and the coordinate of point B, xb, yb and zb. Here, as can be seen, a position vector is drawn from the point A to point B, or in other words, vector RAB is directed from point A to point B. So here the question is how to obtain vector RAB in terms of the coordinates of the points A and B. So referring to this vector triangle, obviously we know that vector RA is added with the vector RAB in a head to tail fashion, indicating that as per the vector triangle rule, we have vector RA plus vector RAB is equal to vector RB. It does mean the position vector that is directed from point A to point B will be vector RAB, that is equal to vector RB minus vector RA, which indicates that any position vector which is directed from point A to point B can be directly expressed in terms of the position vectors associated with the respective points. So from RAB is equal to RB minus RA, we can write down the position vector RAB as xbi plus ybj plus zpk, which is nothing but the position vector associated with the point B, minus xai plus yaj plus zak, which is the position vector associated with the point A, which can be finally written as xb minus xa into I plus yb minus yaj plus zb minus zak. So the important thing is that the position vector directed from point A to B is equal to position vector associated with the point B minus the position vector associated with the point A. Now let us see where the concept of position vector finds its application. In many of the three-dimensional problems in engineering mechanics, we need to specify the direction of a force. So the direction of a force is normally specified by providing 2 points through which its line of action passes. For example, as you can see, a typical application of the position vector is demonstrated here, wherein you know that a fixed reference axis xyz is given, and for example here a plate is fixed to the wall using a hook arrangement and a force F is applied. Now to specify correctly the direction of force vector F, we need to mention 2 points through which the force F passes. For example, in this case, it is clear that the force F passes to the points A and B. It does mean that we can express the direction of a force F by specifying the unit vector along the direction AB. Now the question is how to obtain the unit vector along the direction AB. It's very simple because we know that the unit vector along any specified direction can be obtained as the vector divided by its magnitude. For example, in this case, we can use the position vector directed from point A to point B, which is marked as vector R in this sketch. Obviously, we know that by our basic definition, vector R is nothing but it is a position vector directed from point A to point B. Okay, so accordingly, we can write down vector F as its magnitude. So the magnitude is taken care multiplied by the unit vector in the direction AB, which will help us to specify the direction of vector F. So this can be written as F into, now the unit vector along AB is nothing but it's a position vector directed from A to B divided by its magnitude, which is equal to F into, we know vector RAB from our earlier discussion, it must be XB minus XA into I plus YB minus YAJ plus ZB minus ZAK divided by the magnitude of this position vector, which is nothing but the square root of XB minus XA square plus YB minus YA square plus ZB minus ZA the whole square. Now we shall illustrate the application of the position vector to a simple practical problem. So let me first read the problem statement. So the roof is supported by cables as shown in the figure. If the cables exert forces FAB equal to 100 Newton and FAC equal to 120 Newton on the wall hook at A as shown, determine the resultant force at A and express the result as a Cartesian vector. So referring to this sketch, so as can be seen, so here we can say that this exert, so we have the two cables, right? So this is a roof. Okay, so as you can say that this is the roof, right? What is marked in a light gray black color is the roof, and as you can see that this roof is hung from the point A on the wall using a hook, and this roof, it is tied to the point A by two cables AB and AC. So it is found that the force in the cable AB is 100 Newton as shown here, FAB is 100 Newton, and the force in the cable AC, which is obviously due to the self-weight of the roof, is equal to 120 Newton. So as you can say that AB, it is directed along AB, and the force in AC is directed from A to C, right? We are also given the location of the various points that will enable us to determine the position vectors associated with the various points. So we are asked to find out the resultant force that is acting on the hook at the point A, and this resultant force need to be expressed in the Cartesian format. So what we do is that our procedure or the philosophy is we know the coordinate of the points A and B, and this coordinate of the points A and B can be used to define the unit direction along the FAB vector, so that FAB can be expressed in the Cartesian format. In a similar way, using the coordinates of points A and C, we can directly obtain the unit vector along FAC, and thereby we can express FAC also is in the Cartesian format. Now the resultant force is nothing but vector FAB plus vector FAC. It is very simple for us. So the coordinates of these points ABC, as can be clearly seen from the sketch, are 004, 400 and 420. And the corresponding position vectors of these points are therefore given by vector RA. Obviously, you know that as per the definition, any point with a coordinate xyz will have a position vector of xi plus yj plus zk. Accordingly, position vector associated with the point A will be 4k, position vector associated with the point B will be 4i, and position vector associated with the point C will be 4i plus 2j. Now, having defined the position vectors associated with the points A, B and C, we can go for the definition of the position vectors directed from A to B, that is vector RAB as vector RB minus vector RA, that is obviously is equal to 4i minus 4k meters. And now the magnitude of vector RAB can be easily obtained as square root of 4 square plus minus 4 square, which is equal to 5.66 meters. Now we can define vector FAB as its magnitude, which is already given in the problem as 100 Newton. Okay, 100 Newton multiplied by the position vector RAB along its line, that is already computed, that is 4i minus 4k divided by 5.66. Please remember 4i minus 4k divided by 5.66 defines the unit vector along the direction of force vector FAB. So we finally expressed the force in the cable AB in the Cartesian format as 70.7I minus 70.7K. Now let us go for expressing the force in the cable AC in the Cartesian vector format. Obviously, this requires first of all the definition of the position vector from point A to C, which can be defined as vector RAC as vector RC minus vector RA, that is equal to 4i plus 2j minus 4k meters. Obviously, the magnitude of the position vector RAC is obtained as square root of 4 square plus 2 square plus minus 4 square, which is 6 meters. So, the force in the cable AC can be written in the Cartesian format as its magnitude multiplied by the unit vector in the direction AC. The unit vector in the direction AC will be vector RAC by magnitude of RAC. So that's equal to the force in the cable AC is given as 120 into 4i plus 2j minus 4k divided by magnitude of RAC is obtained as 6 meters. So this happens to be 80I plus 40j minus 80k newtons. So we obtained FAB and FAC in the vectorial format. So it is easy for us to obtain the resultant force that is acting on the hook. Vector FR as vector FAB plus vector FAC. Adding vector FAB and FAC, which are already available in the Cartesian formats, we obtain the resultant force as 151I plus 40J minus 151K. This is what is indicated in the sketch. So as you can say that this is our vector FAB and this is our vector FAC, and obviously you can complete a parallelogram, and the diagonal of this parallelogram will represent vector FR whose expression in the Cartesian vector format is given already here as 151I plus 40j minus 151k. So that is all our discussion regarding the position vector. We will start our second other class with a new topic. So till then, have a nice day.